Well, thank you all for inviting me to this talk. It's a good way for me to close down a Friday because after I do this, I'm going to take off. I had hoped to be there to deliver this to you in person, but certain things happened, and I guess it's convenient to have the Zoom things in place now after the pandemic. Are we even over the pandemic? What I want to talk to you about is some climate controversies going on and my role and work in this field that tries to rectify some climate controversies through change points. So I'm going to go through a general expository talk on change points. Now, I know a lot of you won't have a great statistical background, so I will try to communicate the topic more through graphics than mathematics, but I will be giving you some mathematics just to show you how it goes. Before I get going, this is joint work with Thomas Fisher, who was formerly at Clemson, Shanghang Li, who was formerly at Clemson, and Michael Robbins, who was formerly at Clemson. So these are all three former PhD students. All right. For an outline of the talk, I'm going to tell you what a change point is. I'm going to tell you how to test for the presence of a single change point, and then we'll get into the problem when you have multiple change points. I'm actually going to take you through a climate homogenization walkthrough where we take a look at an actual series and see what's happening. I may or may not give you a simulation study, and then I really want to close down this talk with the huge controversy, which is about hurricanes and tropical storms that is going on right now. I cannot see the audience here, so if you've got anything, if you raise your hand or something, can someone call out questions to me? Okay, I'm happy to take questions as we go along. Just say, hey, stop. I am planning for about 45 to 50 minutes and then letting everybody go get the pizza, but I'll take questions for as long as you want to ask them as well. Is that okay, Jim?
It's absolutely okay.
All right, so let's really get going. What's a change point? A change point is something that drastically and abruptly shifts. Think of a discontinuity. So maybe the speed limit out on Interstate 85 got raised from 55 miles an hour to 65 miles an hour, and you're studying highway traffic depths. That is called a change point because something abruptly changed. Now, I want to show you that I'm going to give a talk about change points and what they can do and how they can really fool you and what we do to sort of combat the change point problems. Now, I think one of my favorite graphs is here, and I think that this really illustrates the problem. These are annual temperatures at Tuscaloosa, Alabama. Now, I chose this because I'm from Auburn. I did my undergraduate at Auburn, and anytime I get to poke fun at the University of Alabama, I will do such. But these are 100 years of average annual temperatures from 1900 to 2000 there. And you can see that these are in degrees centigrade, and the roughly the average temperature in Tuscaloosa year round is like around 58, 60 degrees there, somewhere in here. Now, in this record, over 100 years, we're really interested in climate trends. Okay, you may have heard that we're sort of warming up. Well, look what happens to this record. There are two very pronounced features here, one in the late 1930s and one in the 1950s. And in this case, for this series, I actually know what happened. Okay, in the late 1930s, they moved the temperature recording station of Tuscaloosa from downtown out to a colder river location. I think it's the Black Warrior. In the 1950s, they changed the thermometer gauge. I believe it was 1956, and things got a little colder. Look what can go wrong. Okay, if you were to just get from the National Weather Service this 100 years of data and fit a line through it without accounting for these two break or change points, you would conclude that the slope of this line, this is the best fitting line, is slightly negative. Now, it's not statistically significant negative, but you would conclude that Tuscaloosa is actually cooling. Now, look what happens if you put a line, but you allow shifts in that line where you move the station or change the gauge. All of a sudden, the trend slope comes out to be about 2 degrees centigrade per century, which is considered rapid warming. So we have a huge issue here. Well, how bad is it? Most of the time, we do not know where these change points lie. On the average, United States temperature series experiences about 6 candidate breakpoints with station moves, instrumentation changes, and a whole host of other things that can happen. I want to show you another slide that is 180 years of temperatures from New Bedford, Massachusetts. And this is sort of the same issue, but the opposite pattern, in that if we ignored all the possible breakpoints and fitted a line through the data, we would have concluded that New Bedford is actually warming. Whereas if we allowed for shifts in the record, okay, and put things in there, then the slope is actually looks to be cooling just slightly. It doesn't look to be cooling all that much. Okay, so these change points now, 30 years ago, climate people were just starting to understand the effect of these change point discontinuities. They occur all the time. If you've ever gone jogging at night and gone through a neighborhood where all of a sudden got a couple degrees cooler, you know what I'm talking about. These are very, very common. Typically, you have about 4 to 6 change points per century that could go, each of these shifts could go up or down a couple degrees, and you're trying to figure out what the long-term warming or cooling rate of the series is. So this is a big problem. In the modern days, now almost every country has what we call a couple climate time series homogenizers, whose job it is to hunt for these discontinuities, take them out of the record. And let me say that it's very controversial on how to do that. Okay, but the rest of this talk, I'm going to walk through some examples and the controversies that arise and give you a little bit of feel for the change point problem. All right. The key statistical questions when you're given a record and you're going back and retrospectively looking for change points is how many change points are there and at what times do the change points occur? If you know those two things, you can pretty much answer most any statistical question that you want to answer. Now, I'll list some references here. Unless you're really interested in this problem, they probably don't mean much, and I'll flash them again towards you at the end of this talk, or give them to you if anybody's actually interested. But these are some change point references that you can read much more about this problem. Okay, so the first thing that we do, that a statistician does, is we model the world, and we would like to explain what we see in the data. And here's what we do. X of t is the temperature. And I'll think here, I'll work with yearly data, and I'm just thinking X of t is the temperature at year t. It's some overall mean plus a delta t. And this delta t is going to represent piecewise linear means. It's going to be a step function. The epsilon t will be random error. And this gets us into the role of statistics because statisticians quantify random error very well. And what this is called is a time series model with mean shifts. Okay. We call mu the overall location parameter, and that could be considered as sort of the long-term temperature. In Clemson, it's about like Tuscaloosa, somewhere between 55 degrees and 60 degrees Fahrenheit. Let me say a little bit more in this model. The shifts. How do I parameterize the shifts? Okay, M in this talk will be a very important parameter, and it will denote the number of change points. Okay. Until we get to the first change point, which will occur at time tau 1, there will be no shift in delta t for the changes. But once we hit tau 1, the temperature shift by delta 2 degrees. Then we come to the second change point where things shift by delta 3 degrees from the original. Okay, and so what this is just nothing more than we call a piecewise mean function. You can have piecewise linear functions and things, but here's what's really important. The model is for M change points that occur at the times tau 1, tau through tau M. We don't know M, we don't know the taus. We do know the series length capital N. Okay. When a statistician goes to model temperatures, we know that temperatures are correlated. I used to love the fall in Clemson because you'd get these long sunny stretches in October where every day for about a week would just be a perfect low humidity day. And, you know, one day it seemed to be a carbon copy of the other. Statisticians call that correlation. Okay, without saying too much here, the errors are taken to be a zero mean causal autoregressive process. Now, if you've taken a course in time series, this is the standard time series model, but you've got to take is it math science 809? I don't know. How are you guys divided? You all bifurcate there a lot, right? There's two schools now. But what I want to say is a standard time series model, and that if you ignore correlation and change point analyses, you can actually get into a good bit of trouble, but I won't belabor that point here. Now, I want to show you, let me try to explain this with a graph. These are Central England temperatures from 1900 to current. And what we see, what I would like to do next is show you how to go about detecting a single mean shift. Now, for this talk, what the mean shift here, actually our most probable candidate for a shift in the record occurs at 1988. And what you see is the sample average temperatures. Over in Britain, they use degrees centigrade. So it's 10.22 degrees centigrade. And before 1988, the average data was 9.45 degrees centigrade. So right there in 1988 was my biggest discrepancy. But this sort of tells you what we do to find a single change point. We take a time, and we're going to take all candidate times before and after the change point. We compute a sample mean before the change point and after the change point. We look at its difference, and then we assess whether or not that is statistically different from zero. Okay, so let me give you a little bit of theory on how to do this. This is the theory for one change point, and it's sort of cool because we get into some gnarly mathematical methods very quickly. Okay, suppose that you're running along and time k is the time of the single mean shift. So what I do is I compute the average of all the data before time k and the average of all the data after time k. And you would conclude that a change point at time k exists if the absolute value of this difference is too large to be explained by chance variation. Well, I've got to explain to you what chance variation is. And so let's do that. Okay. Now, there's a little complication here because the data segment starting from the record up to time K has K data points, and the second segment after the time K has N minus K data points, and those two may not be the same. So statisticians scale for the number of points, and what this amounts to doing is taking this discrepancy statistic dk to be this is a scaled difference between the sample means of the two segments. Now the sigma hat here is what we call a sample standard deviation of all the data points. But what I'm going to do is if at time k, if time k is a change point, dk should be somewhat large in absolute value. Now here's the deal. I don't know that time k, I don't know the time of the change point. So what I do is I take the largest value of dk. I take the largest one, and that's sort of telling me that is going to be the most likely time of a change point. And this is what I have called Q. And this is a maximal statistic, and maximums scare statisticians, but there is actually a famous result. If any of you have gone through 803 and 817, there is a result that says as the sample size goes to infinity, that Q converges to the supremum of a Brownian bridge process. Okay. Now, Brownian bridge is made from Brownian motion, and Brownian motion is that stochastic process with Gaussian distributions pioneered by Einstein, and it's probably its most famous characteristic is the sample paths of Brownian motion are functions that are continuous everywhere and yet nowhere differentiable. How about that? You get sort of like that Cantor type behavior from the sample paths. But what I'm trying to say is if this maximum of the absolute values of the dk is bigger than 1.3, with 95% confidence, you can declare a change point. All right. So this was the place where the maximum decay happened, 1988. All right. And if you look at the absolute values of the decay, they peak right here at 1988. 1.3 was the 95th percent threshold. So we would actually conclude that there is a change point in the Central England record and that things have shifted. Does anyone know what might have caused this change point in 1988? Don't all speak at once. You can unmute yourself. Well, when you think about things and the Industrial Revolution, we started pumping carbon dioxide into the atmosphere in a grand scale in the 1940s, 1950s. And if the data starts going up in the 1940s and 1950s, what you're going to see if there's an increasing trend is when we put a model in there that doesn't have a trend, it's going to signal a change point right in the middle. So this change point is generally explained by global warming. Okay, and this means that our climate is not stationary, but you probably knew that already. Okay, let me stop here and ask if there are just any questions here. I'll leave it on this slide. I'll do this talk in stages.
All right, I got one. Sorry,
Sure.
I just want to clarify. So when you say that there's this change point detected around 1988, it doesn't necessarily mean that something specific happened in 1988. Like it could be like
No.
Okay.
No. Okay. And indeed, some change points are caused by station relocation. Other change points we call these natural change points and artificial change points. And really, when we go to change temperature records, we only want to change them for artificial change points. So this would be something that climate people would go back. They allow me to find the change points, and then they would go back and say, well, I believe that this change point is showing up because of global warming. And then they might actually put a model with a linear trend in here and see if that takes away the change point. Now I happen to have done that, and I know the answer, and it does. Okay, we've been warming rapidly in central England since about the mid 19th century. Anything else?
Yeah, go ahead.
So just kind of a more general question, I guess. I'm assuming it is a thing that people have done, but when you're looking at this hypothesis testing for change point models, do you also kind of look at spatial variation, try to pull that information in there? Like if you see a big gap somewhere, but then you have nearby stations without a big gap, you can assume it might be something measurement related?
Yes, that's a very good question. And I'm making things very, very simple. But when we do, when climate people actually change, say the Clemson record, what they will do is they will subtract the Clemson record from, say, the Greenville record, the Anderson record, the Walhalla record, many, many towns nearby. And they hope by doing that, that they will subtract out things that naturally influence both the stations. Okay, so I'm being a little bit, there's much, much more to this. You can make an entire living being a climate homogenizer now, but I'm getting to the mathematical simplicity to there. So the spatial statistics is actually using what we call target minus reference series. We don't tend to have typical spatial models because if you're a spatial statistician, the nice continuous models that you'll see in a spatial statistics class don't tend to really apply that well here to this scenario, but that's a real good question. Right? Unless there's anything else, oops. I need to now go to the multiple change point case. And I only have about, well, I've got a couple slides of math here and there, but there's only this is the most arduous slide in. The problem with multiple change points is very, very much harder than a single change point. And there's a variety of research that has been conducted over the years, including at Clemson. Statisticians, when they fit models, what they try to do is they compute these things called the likelihood function. And the better fit, the higher the likelihood. The more parameters you have in a model, the better the fit. But once you allow too many parameters, the fit doesn't get better, but you're sort of using too many parameters. And the way to handle this is what we do is we take a likelihood. So if you were to have a model that has M change points that occur at tau 1 through tau M, L star is the best likelihood that you can achieve from that model. And then I am going to charge you for having M change points at the times tau 1 through tau M. So here you've got to pay for everything that you use. Okay. In the modern statistics research is a whole bunch of things about this penalty. There are many different forms for what the penalty should be. There's a common penalty called the Aka-Icke information criteria, which says the penalty for using M change points should just be 2 times M. The Bayesian information criteria says that it should be M times the log of the series length. Now, it takes a lot of information theory, and I don't even think we teach information theory at Clemson, to understand where these two penalties come from, but they're both proportional to the number of change points. And they tend to do poorly. Okay, a better penalty is called the minimum description length. Okay, and what this does, this penalty is a little more exotic than just some multiple of the number of change points. It actually accounts for where the change points are. You see that tau I minus 1. So if you want to place two change points really close to one another, the penalty for that will be a little bit more severe than placing the two penalties that are sparse. Now, I did not invent the MDL, but this came from 2006. I've suggested even variants of MDL to improve things. All right, so now what I want to do is I want to take you through a climate homogenization. How many segments do you see in this series? Okay, this series, no trends. Okay, I'll tell you that it has no trends. How many different segments? And let's go back to the Tuscaloosa. So I'm thinking here with a trend, this had 3 segments or 2 change points. How many change points you see in this series? I need a number.
3 or 4.
3 or 4. Okay. Anyone see more? Well, let's go through. These are precipitations from New Bedford, Massachusetts. Okay, and let me just tell you that in terms of annual precipitation, climate people tend to model the log of annual precipitation as normal. And so what this means is the log of XT is a what we call a normal process. And so this sets what type of likelihood I'm going to use. Okay, the penalty for this is the MDL, and I'm going to walk you through what the MDL does on this series. Okay, so here's what I did. I went and I fitted all 1 change point candidate models, and it concluded, MDL told me that the best breakpoint was in, I think it was the late 1960s here. Okay, so that's a 2-segment model. Now, then I went and fit 3-segment models. You like that fit better?
No.
Looks a little better. Do you think I need to go further?
Yes.
All right. Now, I want to tell you that there's a huge computational bottleneck, because if you have a series that's 180 years long and you're going to place 2 change points, this calculation was done exhaustively. So 180 choose 2 different time series models that I had to fit. And each of those optimizations, time series optimizations, probably took a minute or 2 themselves. So this was quite a chore on my laptop, okay, to fit this model. So there's the 2 change points. What do you think? There's the 3 change points. You seeing more? Well,
Maybe very beginning. I don't know.
let's take a look. Here's the 5-segment model. Can anybody see a difference between the 4-segment and the 5-segment model? Okay, 4-segment, 5-segment. Look really, really close here. MDL put a segment of length 2 there. Now, why did it do this? We had to go back to the record books. Okay, so first of all, MDL is based on information theory. And what this was flagging was a pattern that was very irregular. MDL will also pick up on outliers. It turned out that New England was under a historic drought in the late 1960s, and this change point made total sense. Okay, the 6-segment models. Now, think about this. 182.6. That is a huge number. And to do this optimization took me 2 months on my laptop. It would have only taken me a month, but if Jim remembers my dog Angus, it was almost done and he stepped on the laptop and crashed it. And I had to start it again, but it took about a month to get this simulation done. The 6-segment model, it put a 1 segment right there. And let me show you the table. Okay. So these are the MDL scores with the change point times and the number of segments. Minus 309.8570 was the winner. It included that very, very short segment. How about that? So it actually wanted, MDL tells me that there is something going on there for just 2 years. And in fact, a lot of these methods are applied to clean up the United States data. I can't tell you how many times MDL has flagged a single data point that has actually been misentered by 10 degrees. It happens very, very frequently to those people who are entering this data and digitizing it. MDL finds it. It's one of the great quality checks out there. Okay, so the best model actually had 4 change points, 5 segments, one of which was a very, very short segment. Okay, comments or questions?
So in general, is the MDL measure just not super robust to heavy tails? Or is that somewhat a good thing for a lot of informed outlier detection?
Well, the MDL I devised for this works on the fact that the data, the log of it is Gaussian. So if there's a departure from that distribution, I'll law a heavy tail. The MDL is going to tell me about it. Now, that said, log Gaussians, if you take E to a Gaussian, that's called a log normal distribution. And it doesn't, it actually has a pretty doggone heavy tail. So even with that heavy tail, there's an outlier there. That,
Is there a misprint in your table, or did 1917 appear as a change point and then disappear?
yeah, that looks like a misprint, doesn't it? Yeah, it should have been the change points that show up should have been there. So the first one should have been 18, late 18s. Then what does that look? 19 something there, right?
Yeah, but there was like a 1917 in the second iteration, and then it was 1910 after that. Is that possible? I haven't.
Oh yeah. Don't believe that the change point times won't move around. Okay. In fact, in going from say 3 segments to 4 segments, you have no guarantee that that the 2 change points that you found for the 3 segment model are going to show up to be the same as the change points in the next higher model. So that doesn't happen at all. And that's what's going on there, Jim.
Yeah, it's kind of weird though in that table, because 1917 appears to be the only change point that appears and then never reappears in your iterations.
Yeah. What we say for this is that this is basically what happens is this MDL objective function is not convex, and how to optimize it. I've given whole talks on that. The techniques here that we use are something called genetic algorithms, which are very, very smart random walk searches that are unlikely to visit. They're random searches that sort of go in and out and mutate and take good models and breed them, and they have children and whatnot, and we converge to the optimum. But it's a very, very tough optimization problem, one that Warren Adams probably would not appreciate.
Yeah, and I take back what I said, because 1965 disappears as well, but
Yeah.
1967 is very robust.
Yeah. Yep. You know, I could show you some simulations, but let me let me get to the controversy for the sake of brevity. I will tell you that what we do, I actually showed you how the methods work on data first, which is rare for a statistician. But if I were going to justify this, like what this simulation shows is that when I have trained these methods on a sequence that looks just like the New Bedford data, but I know has no change points, in 1,000 simulations, the methods tell me that there are 0 change points 990 out of the 1,000 runs, and that's pretty good. Okay, so this stuff I will skip here and get to the controversy, but this MDL is actually pretty doggone good, and I probably spent 10 years of my life at Clemson and a couple PhD students going through things that would handle the and improve MDL things. But I want to get you to the last part of this talk, which is the controversy. We believe we're in a warming world, okay? A hurricane or a tropical cyclone is nothing more than a storm. You know how in South Carolina, you get a hot afternoon in the summer and you get a thunderstorm? Well, that's the Earth trying to keep the atmosphere at a constant temperature. The way the Earth does that as a whole is it produces tropical cyclones that come out of the tropics, and then they move up to the Arctic, and they carry heat. It's the way the Earth sweats. So in a world where there is more warming, there is more energy to dissipate. And folks believe that there will be either more tropical cyclones, or possibly they'll get stronger, or maybe even some combination of the two. Okay, here is the tropical cyclone record in the North Atlantic. This is a little bit of a busy graph. It goes back to 1850. So for example, the dark shaded counts here in this graphic are the really heavy hurricanes. These are category 3 and above hurricanes. And those are the big storms. And you can sort of see it looks like they've been going up in time. Okay, just the tropical cyclones. A hurricane is a tropical cyclone that gets to 75 miles an hour wind speed. So I've done this graph. You can sort of see that the number of storms are going up. Well, in the past, climate people, until recently, have always been telling me and other folks that there should not be any more storms, but they might be getting a little bit stronger. And this has become a huge controversy because there's various camps suggesting various things, and we don't know. I was amongst the minority 10, 15 years ago when I was saying, hey, I am not seeing what the climate models are producing in the statistical record. But we had a climatologist named Kelvin Drogemeyer who testified in Congress that hurricanes will become stronger, but there will not be more of them in the future. And then I had to go say, well, I don't see that at all. Okay, the rationale for Drogemeyer's statement was that he was looking at a lot of simulations in global climate models. One of the things that I know from global climate models and PDE analysis is that they handle tropical precipitation very poorly. I like to also say that Kelvin Drogemeyer was Trump's science advisor, and as you know, Trump poo-pooed a lot of things on climate change, not to say which side he would sit on in this, okay? There's a really cool book going through this controversy, 2007, Storm World. If you want to read who knows what, including a lot of my friends and where they sit on this controversy, it's an interesting read. It's not the best book in the world, but it's sort of cool if you want to see scientists mudsling at another. All right. So what do I know about tropical cyclones? These are well modeled by a count distribution that we called Poisson. Now, I won't get into justifying my model, but the Poisson distribution works very well. We'll take a Poisson model with no trends, but mean shifts, and we're going to see how this works in segmenting up this record, and we'll see what happens. Now, a lot of the major journals have been very receptive. This is Annals, and both Annals and JASA, two of the best journals in my field, have published stuff on our work on tropical cyclones. Okay, so if you forgot the Poisson distribution, the probability of getting a count of k is e to the minus lambda, lambda to the k over k factorial. This goes from k is equal to 0, 1. It's a true count. And what we model is x of t is independent, but we let the Poisson parameter change. The mean of a Poisson with parameter lambda is lambda. And what I'm going to do is I'm going to let the lambda parameter just shift at each change point time. Okay. And that's my model. There's some calculus that you can do exactly that makes this not a very hard optimization problem at all. This one is much easier than the last one because you can get simple calculus optimizers and you don't have to do numerical searches to minimize likelihood, negative log likelihoods, or maximize the likelihoods. I'm still using the MDL penalty, and let me show you what I find. Okay, this is the total count segmentation. Going back to 1800s, what did we find? 1, 2, 3, 4, 5, 6, 7 change points. This record is anything but homogeneous. Okay, I see something there that the climate people don't really like it when we flag these outliers. And what these two are sort of telling me, these 1 point things, is that maybe there's some differences from the Poisson model that I'm using. So what we did is we refitted this and we allowed the segments to be at least 5. We imposed that the segments are at least 5 years long. And this is the segmentation that we got. Now, this is really starting to get interpretable. So the hurricane record was what it was until about the 1930s. In the 1930s, we had the onset of aircraft reconnaissance, increased shipping traffic from World War II. About that time, there were a lot of storms that would form over the open Atlantic Ocean, weak storms, and spend their entire lives without being detected, were suddenly being detected. And so people regard this shift as being somewhat of we're improving our surveillance systems. In the 1950s, you see that we shift down. I'm not sure we have as good an explanation for that, but the one that we're all arguing about is in 1995, we went to a hurricane regime that is larger activity than anything that we've seen, and we haven't gotten out of it yet. Now, this study goes through 2019, and in 2006, we ran out of letters, Roman letters, to name the storms. This also happened in 2020, and 2021 is checking in. I promise you, we haven't got out of this regime yet in the 2 years it's been since we did the study. Okay, so we increased. One might argue that say, okay, that was all tropical cyclones. What about just the big ones? And what about all hurricanes and major hurricanes? Well, here's the segmentation for hurricanes. Hurricanes is 75 miles an hour or more. Anybody know? I believe Cat 3 hurricanes, the wind speeds got to get to about 115 miles an hour. So here are the segmentations for those. Again, you see a couple outliers and a lot of change points here. We don't conclude anything there, but if I go back and I restrict to get rid of the outliers, look what change point comes up again and again. Okay, we're getting more hurricanes and we're getting more stronger storms. Okay, and the change point here is again 1995. There with the stronger storms here, you see that we repeal that 1930 change point. That sort of makes sense because you know, if the storm was really strong, probably we would have known of it. If you had a storm even in the 1930s where you got 113-mile-an-hour wind speeds, 115, you would probably know of it. Okay, so what we're seeing here is that recently we have gone to regimes where we are in increased hurricane activity. Okay, and we have yet to get out of that. Now, climate folks will also look at something called accumulated cyclone energy, where they will trace out each hurricane that occurs in the season, and they'll follow its path every 6 hours, and they'll get an estimate using how big the storm it is and stuff, the energy that the hurricane season is dissipating. The change point here again is 1995. The objective function we use here is Gaussian. It's probably not a very good one because with all these spikes, I don't think that this data is really marginally Gaussian, but we do get, again, the 1995 change point. All right, one last thing. Storm wind speeds. We went and analyzed those, and try as we might, with all our change point might, we cannot find anything. Now, we talked to the director of the National Hurricane Center, and we told him, hey, he's actually got the coolest name, Landsea, Landsea, and he's a director of the Hurricane Center. He named his first kid Aaron Landsea. Get it? No, whatever. Okay. But when we talked to Landsea, he told us, well, I'm really glad you haven't found anything in the storm wind speeds because, and I said, no, well, we found something right at 1900, but that was it. And he goes, and he laughed and he said, well, here's what's going on. We take all the hurricane wind speeds and we've actually reanalyzed that data going into wind tunnels, and we've modified, like for example, Hurricane Camille, when it came across in 1969 at Pass Christian, Mississippi, the original estimate of the wind speed was 210 miles an hour for a landfalling wind speed. Our modern best guess is 180 miles an hour. Well, Landsea told me that they have gone and reanalyzed all the data 1900 to current, but they didn't do things before 1900. And sure enough, we found that change point, but we don't find other change points, meaning, hey, we're probably not going to find changes in the storm strength. So basically, we find the exact opposite of Dragemeyer's claims here. Now, that's basically it for the talk. If you're interested in these type of problems, their applications in science, I have 3 pages of things that references on this topic, including the only thing I'll note here is what is really cool is that the Journal of Climate, do I have any Journal of Climate reference? Yeah, Journal of Climate has always been really good to me in terms of hosting our work and trying to get the change point things out to the climate community so that we can better analyze our data and make conclusions. Okay, so I'll stop there and take your general questions.
Let's thank our speaker first. Thanks, Robert. Questions?
It can be on anything too. Like, did you all notice my Clemson hat?
All right, I guess I'll give it a shot with a slightly less general question. So when we were looking at change point models earlier for those temperature time series, we were always kind of looking at average temperature, like over the course of a day, maybe over the course of a week. How sensitive is that to the kind of temporal resolution we're looking at? Like, do you see the same change points generally if we're looking at like, say, midday temperature versus average daily temperature overall?
Right, right. So I only gave you the theory for annual temperatures. And you know how we get annual temperatures is we average up daily temperatures, and the daily temperatures are the high plus the low over 2. And I could explain why we take those definitions some other time. But there are change points in the variance of sequences. And this is really important in the finance community because they have an entire theory on volatility changes. There are change points in the marginal distributions. If you're looking at precipitation and you have, say, a point mass at 0, it gets really complicated if you're getting more dry days without rain. So you can have change points in a lot of things. I just did change points in the mean here. I've written change points in just general topics on general distributions before, but this was a talk on in the climate sense. We're more interested in changes in the mean. Now, the latest hot off the press article that I was working on a revision considered both changes in the mean and the variance. And if you do the mean right for a very long temperature series, you almost never see changes in the variability. Okay, so most of the action with the temperature series lies with the mean.
Very interesting, thank you.
I have a question sort of inspired by your answer, and that is, so when you watch the weather on TV or whatever, and they say, they give you an average temperature, is that really, do they still do that high plus low over 2?
Yeah, the reason that they did that, Jim, was in the old days, we had a lot of automated observation systems, and you can imagine a temperature gauge that pushes a needle down to the low temperature and another needle to the high temperature. So somebody didn't have to visit the station more than once a day. And that's why we use high plus low over 2 to this day.
Well, it's interesting because I would think that, nowadays, I would guess that basically they could take the temperature every second, right?
Right, and use an integrated average, and that would be a more accurate mean temperature. That procedure in itself and how to measure temperatures has its own controversies as well. People who look at that are called metrologists. And they can talk your ears off about that one. As we move to more modern observation systems, we also find that there's more change points and more advances in the technology to measure temperatures as time goes on, and not less change points. So the change points aren't becoming any fewer. That's for sure.
So let me ask you, this is kind of maybe an opinion guess question, but if tomorrow they started measuring temperature that way, so the more accurate, they take the temperature every second and, basically do average value function, so to speak. Do you think that would cause a change point, or would the noise cancel out or come close?
Nope. It's going to cause a huge change point. In fact, when Canada went from the metric system, the US, to the imperial to the metric system, I can pinpoint that change point almost in every series. How about that? So if you change how you measure it, something with that drastically, yeah, you're going to be able to see that. Places, if you were to take an integrated average, well, there's all sorts of, in the United States, diurnal cycles and stuff. So depending on where you are would bias things certain ways. We also know that different types of temperature gauges give different types of responses. The standard temperature gauge was called a cotton region shelter for so long. And there are all sorts of ways to measure temperature, and the right ways and the wrong ways to do this that math people like myself would never get into. But it is interesting to talk to these people because it's not settled to this day.
Very cool.
But I'll also challenge you to, next time you go to Walmart or Kmart and look at a rack of thermometers, you'll notice that Even these independent and identically distributed ones, you'll get changes of a couple degrees each, you know, as you look from gauge one and you thumb through the gauges, all there in the same rack, you can be off easily a couple degrees there. There's that much variation.
Do you remember those old thermometers that had the mercury in them?
Yeah.
You
Yeah.
know, those thermometers only went to 40 below, and I bet you know the answer why.
Well, I mean, I don't know what mercury does at -40, but it's probably going to become pretty sluggish.
Yeah, actually -40 is the freezing point of mercury.
Is that right? -40 is also the point where C meets F, and it's also the coldest I have ever seen. And that was in Yellowknife, Northwest Territories. It was cold.
Oh, yeah. Other questions? How about you all out there in Etherland? Any questions?
I see Matt Saltzman on there. Hey, Matt.
Hey, Robert, how's it going?
Pretty good. How you doing?
Oh, we're surviving.
Let's thank Robert one more time.
Yeah, I'll let you guys get to pizza, or do I need to hang out or what?
No, it's cool. Yeah, you guys, and you have to take the pizza.
Oh, I do?
Oh, and Robert, by the way, Z told me to tell you hi.
All right, we'll tell her hi back.
Right. Let me know when you're actually physically going to come to town.
Oh, will do. Will do.
And thanks a lot for doing this.
Thanks for the invitation, folks. I wish you a great weekend too.
Have a good weekend, everybody, and we will see you next week.